So there's a newly retired professor. His name is Richard Gray. He's published a very encyclopedic work on classifying stars. So Gray and Corbally is kind of currently a well-known resource for figuring out how the MK system works, and he has done developed software in order to make the system more accessible and automated. But he's an expert in this and was part of the later part of the committees that actually finished the work. So he was a professor at Appalachian State, and he's newly retired, so he's a professor emeritus. And this star that he wanted to look at has been sort of a problem that had remained of interest to him for the past 15 years. Somehow he didn't have time or the resources with grad students in order to pursue this. So he put together a project. I'm in this spectroscopic group that meets every other week. It's people that have been doing spectroscopy as a hobby for over 10 years, probably 15 years, and most of them are astronomers, either current astronomers, professors, newly retired professors, and then a few just dilettantes that like to dabble in spectroscopy. It's something that they like to do. It's a passion of theirs, and they've spent the money. They have their professional grade telescopes and all kinds of spectrographs. Anyway, so Professor Gray knows what he's talking about. He knows what he wants to do. It's kind of hard to put this in proper order, but there's a star called HD 5501. It's in the constellation Cassiopeia, and he wants to understand why the variability in the light curve is going on. He doesn't understand it, and it's sort of just been a little bone in his teeth for 15 years. So that's what he wants to do, and he thinks it's a spectroscopic binary. He thinks there's a mass exchange going on between the two stars, and that there's a hot spot, and maybe there's some variability due to the hot spot kind of wandering around. So he wanted this covered photometrically, and it turns out photometry, I didn't know anything about photometry, and I still don't, except that it seems to be fairly important because the spectroscopy and the photometry go hand in hand, as you well know. You can get calibrated spectra that way, where you get actual energy description of the star and that sort of thing. And so it turns out to be a really big piece of this project. And the photometry that he's looking for is in the BVR. So this is my faint acquaintance to photometry. And it turns out that you don't need anything as sophisticated as an L high res 3 and a 16-inch telescope and all that. You can do it with fairly modest equipment. You just need the right set of filters in order to get it done, and then some cameras in order to capture the data, and some software, and you're on your way. It's really simple, except I refuse to do it. So Dan, if you want to come, be happy to have you on board. Anyway, so I mentioned that this star is in Cassiopeia. It's a SB1 type binary, so you don't see the two lines moving. You only have a little bit of wiggle in one of them. It's at 3,000 light years. Its primary is 8.5 times the mass of the sun. The secondary is estimated to be at 1.2 mass of the sun, might be higher than that. It's at a visual magnitude of 8.8, almost 9. And then when you get atmospheric extinction involved, we're really 9 or just a touch below 9.1, depending on how thick the atmosphere is at that point. Dr. Gray estimates that it's a B9, which conflicts with the SIMBAD assessment of the star being an A0 type, but I'll go with Dr. Gray. Yeah, and the thing that got his interest was the eclipsing binary. The light curve rather just is not repeatable, which is very strange. Anyway, the star actually turns out to be fairly bright, and it's even though it's magnitude 9, and it's actually somewhat easy to find. And given the restrictions and complications and deficiencies of the GO2 and the finders on the 16, it really helps being able to see these stars in the 50 millimeter finder that we've got. So anyway, so it's in Cassiopeia. It's right in the middle, and just a little bit down. So does everybody know what binary stars are? Does everybody know what spectroscopic binaries are? I hope so, because I can just skip this if we don't have to. Binary stars, two or more stars in a gravitationally bound system. They orbit around each other. Visual binaries have large enough orbits where you can see the two components. An example of those are Mizar, maybe Sirius, Eta Lyra, which is the double-double. You got 4 of them there, and Algol is a binary as well, but it's not necessarily visual. Optical spectroscopic binaries are in very close orbits, and so you can only really see the primary. But if you do photometry on it, you can actually get a light curve on it. You can see the variations based on your observations. So this is kind of what you'd expect to see in a SB1 and SB2 system. HD 5501 turns out to be an SB1. So an SB1 is this guy. And all you're going to see is some wiggling back and forth. Why am I going to this detail? You'll see at the end what goes on, and why it's important to know that you're going to see just probably one, maybe a few lines, if they're really bright, will wander back and forth with the orbits of the stars. So Algol is a nice representation of an SB1. These spectra were downloaded from the BAA website just today. And you can see the hydrogen alpha absorption line kind of wandering back and forth. And so this is a characteristic of the SB1. And on this one, you can just see that there's a little bit of a little nip right here and in this top one. So we've basically got 2 cycles that we're looking at, 2 phase cycles. And you can just kind of get the idea that there might be 2 lines going kind of back and forth as it was shown. You're mainly going to see the brighter star, its absorption line, but you're going to see, what's the right word? They're kind of overlap together and then kind of break apart. So the brighter one will dominate. Convolution, it's the convolution of the light of both lines that you're seeing here. All right, so that's an SB1. This is the light curve of an Algol type star. So you've got a separation between the stars, and you get this sort of very smooth, consistent, repeatable light curve, very consistent over a long period of time. These are more closely, more like active, real light curves. So this is what Algol actually looks like, according to Wikipedia. And so you have to be questioning that just a little bit. But anyway, the point is that they're very smooth, they're very repetitive, they go on and on the same way. Now, Delta Cephas down here in the lower left corner, it is not a binary, but I show this just to emphasize the very smooth, consistent, repeatable quality of this light curve. Each one of these colored dots represent observations by individual observers, and so you can see there's multicolors here, and everybody's kind of hitting the same magnitudes for their observations. So this could be a mix. It doesn't really say whether they're visual observations or whether they're electronic. It's okay to assume that they're electronic because they are so consistent. But the point is it's very smooth. When you come over to HD 5501, what you see here is basically chaos. And this is what caught his attention, and this is what has kept his attention for all this time. This isn't measurement error. This is very, again, electronically collected and very consistent by experienced people, himself included and others. So the data is very solid, and all of this indicates that there's something very unusual going on with the spectroscopic binary 5501. The fact that the period is changing even a little bit, as you can see down here in the 3rd decimal place, very unusual. And it's not smooth. It's not anything like these normal light curves. So that's what he's got us off looking at. And here we are. So this spectrum was taken with the L high res we have, with the 16-inch out at the StarQuest Observatory. This spectra and the 5 others that go with this has been uploaded to the common site, you know, where we're storing all the observations. And so Dr. Gray is looking at this, and they've been presented in our biweekly meetings, and he said they look really good, which is really nice to hear, since I don't do this for a living and really kind of new to the activity. So what we have, let's take a kind of close look at this one, and then we'll quickly go through the others. He insisted that we see the hydrogen alpha emission line and these 2 silicon lines here, because he wanted markers that he could use for calculating radial velocities. And I questioned what this little indentation is here, this minor absorption line, and it turns out this is another handy measurement point, because this is telluric oxygen, and that's from the Earth's atmosphere, and that's going to show up in the same place every single time. So if you need an anchor point, this absorption line at 6516 is as good as any. And one thing I forgot to mention back here, looking at phases. So each of these observations are taken at a specific time, and if you had to display these as they came in on a time basis, you would have years-long timelines, and they would be almost incomprehensible. So you do it in terms of phases. The phases, you know, they repeat, and so if you get the spacing right, you can take all of these observations and you can just stack them up and create these phase charts. So that's what our goal is with the spectra that we're doing. We want to get a minimum of 2 phase cycles, and so that's what this phase number is talking about right here. So it's usually marked as in the previous one. Usually mark phase 0 as either a peak or a valley, and then you subdivide it into as many pieces as you want until you get to 1. So this one's done in quarters: quarter phase, half phase, 3/4 phase, and I've divided up mine into 10 pieces. So 0, 0.1, 0.2, 0.3, 0.4, 0.5, up to 0.9, and then it repeats. So we got the phase listed so that we can keep track of our observations. And then we got these silicon lines, which you already see aren't really quite in the right place. So that's kind of a hint that we're looking at that SB1 characteristic. So that's the first phase. And then the second phase that I got was just about 0.2. And these spectra have been wavelength aligned so that all of the O2 absorption features line up. And you can see that even between these two, you can see that there's some changes, and you can see some of the alignment change on these silicon lines out here. The resolution of the spectroscope in this configuration, it's using the 1200 line grading, and so it has a resolution of just under 4,000, which is considered medium to high in the small spectroscope world. So 100,000s and 10,000s in the professional world, but if you can get up to 9 or 10,000 with the amateur type stuff, you're doing very well. You've got some pretty sophisticated equipment. So the third one, we've got the third one. You'll notice some changes here. It's shorter. It's shorter. So why is it shorter? Because I changed from the 1200 grading to the 1800 grading. And so this is, since the spectroscope was purchased, I'm not really aware that anything has been done with the 1800 line grading. So the 1800 line grading with the 35 micron slit, which is the first time we've used that portion of the slit that I'm aware of, we get a resolution of 8500 with that particular configuration. So it was thought that it would be a better idea to take a narrower view of it and get higher resolution so that the radial velocity measurements would be easier to do. Now you see all these icicles here? These have to do with the fact that it was a bad night when I took these. Clouds were coming in, but even more important than the clouds was the fact that the PC this night decided that it was time to take a rest. And while I was in the middle of the 5th exposure, it quit. I believe it overheated. It thought that I was working it too hard, and so it just plain quit. And the next day it started up. It was rested, it was happy, but not with me that night. And so
It's mad at you.
I don't doubt that.
Would you call it names or something?
I do, yes. Not in polite company, though. So I only got four spectra, four or five spectra for this one.
Yeah.
So I had two more. I was going to do 7 this night. So I think I had 5, and it cut me off early. And it was, it was early in the evening. I mean, it was not 2 o'clock in the morning when this happened. It was like 11:30. It was early.
It was messing.
Very much so. And so this one is a bit noisier. The signal to noise ratios on these top 2 with the 1200 grading and 6 good exposures are actually around 250. And I had to look really hard to come to the conclusion that this one, the third one here with the 1800 and the only 4 exposures, the only 4 spectra stacked, was 117. So it just kind of barely makes the grade if you look at it just right, and you find the quietest part in the spectrum. But this is the configuration that's going to go forward. Since it's in phase order, it's not in the same time sequence that these were taken. So let's see. And then here's the next one. This is again with the 1200 line grading. And you think you're seeing perhaps the second star in this, but Dr. Gray said, no, I think that's probably the hotspot that we're seeing, because the other star is probably something like a white dwarf, and the larger primary star is really obscuring it quite a bit. And so he's thinking that this isn't the second spectra, second star, the second emission line from the white dwarf, but it's probably from the hotspot in the disk, the accumulating disk. And he also points out that if it were, we would be seeing these other lines, these silicon lines doubling, and the only doubling line we see is on the hydrogen alpha line. So, he's got at least 5 degrees. One of them's in astronomy, so I have to take his word for it. And so this one is getting near the end. It's nearly 0.8. And so the next one I have is at a 0.9 phase. And you can just see that it's moving a little bit as well. The hydrogen alpha line sort of moving back towards its starting point. Good resolution on each of the silicon lines here. So we have that. And unfortunately, this one wasn't wavelength aligned. I had a little trouble putting this chart together. So it really should be moved over a little bit to the right. And then this would, this absorption line here would line up better. And then finally, we have the very first one. So the very first one turns out to be at phase 0.952, which is pretty close to 0. And so I put it at the bottom. And this one was taken with the hydrogen line pretty much centered in the nearly 500 angstrom range that we've got with the 1200. And we get roughly half that, as you can see, with the 1800 grading. So it looks different because I didn't get this line. And he said he wants both silicon lines. And so I had to change the micrometer setting in order to get that. But I'll be going forward with this configuration here next time out.
Oxygen doesn't look quite centered in that one either.
Pardon me?
The oxygen to
Yes.
killer oxygen seems a little off in that one too.
So he's saying that he thinks it's a double star, but maybe one star is heating up part of another. Or
No, it's got this mass transfer going on between the two. They're close enough to where the red giant is actually transferring mass into the white dwarf, and he thinks that the disk where it's accumulating, the interface where they transfers out of one star and into the other, is actually being seen as this second line right here. And he thinks that is also the key to the variability in the light curve, as he's seen more of the spectrum. he's coming to the conclusion and looking for more data to support the conclusion that that's causing the light curve to be as strange as it looks.
So the spectrum is helping them solve the keys.
Oh, yeah. It's the combination of the photometry and the spectrographic data. He needs both. And he's getting both. It's there's three groups, us being one of them, one of the three. There's only three groups that are doing the spectroscopy at a resolution of like, around 8,000 and up. The others are doing resolution like 300. So it's wideband, the entire visual. But you don't get this sort of a breakdown. You can't do the radial velocity measurements with that low resolution stuff, but at 8,000, you can do it. So in summary, I just said, we're one of three observatories contributing to high-res spectra. I've contributed 5 at the 3840 level and 1 and going forward at the 8500 level. I mentioned the signal to noise ratios already in the first use. In order to get these spectra, I'm looking at 20-minute exposures at a minimum, and I'm doing 6 of them. That's 2 hours worth of exposures. And that's not bad when you start at, 8 or 9 o'clock. That's okay. And you can even do 30-minute exposures times 6. That's only 180 minutes. That's just 3 hours. That's okay if you start at 9 o'clock or 10 o'clock. But when you start at 11 or 12 because of setup problems, it makes it really difficult in order to get home safely. Yeah, I can get home. It's just, where am I going to end up? In a ditch, in an ambulance? Who knows? So far, it's been okay.
We could get a check written for a bot.
Yeah, no, I already have a cot, and the wife has already mentioned that a couple times. Why don't you just stay? No, I don't want to do that. So that's the last point here. Pushing the limits of the telescope, spectroscope, and the astronomer. I'm not sure that the telescope is providing currently enough accurate guiding. I think that's one of the problems with the exposure times. I think it's oscillating onto and off of the slit as we're going on. That's bad. If I could get that worked out, I'd be a PhD 2 expert, and maybe knowing more about the mount would do. So the smaller the less light you've got, the more accurate your tracking has to be. 35 microns may seem like a large area to get that into, but it's not.
Cloud cover, what's the difference to, can you still get your exposures in 10, 20, 30, 40% cloud coverage, or does it just
No.
wipe it out?
No, the thinner the better.
Yeah.
Thinner the better. And the other night I was starting to get some clouds, and 1 or 2 of the others had some clouds as well. Depends how thick the haze layer is. It has to be a haze layer, it can't be a cloud layer, because pretty soon PhD complains. It says, I can't see the star anymore, so good luck. It'll come off. Yeah, and then with the spectrograph, the limitations are basically trying to get the focus as fine as possible so the light actually is concentrated, and that is an issue. Having to take it off and put it away and set it up again every single time is a consistency problem. So, and we don't have the 2400 grading, thank goodness. It wouldn't be useful in this case anyway, because the range is even narrower, half of what we're seeing. And so it wouldn't work here, but we're using the highest resolution grading we have, stressing the focusing capabilities, and it seems like there's 1 or 2 other things that aren't coming to mind, but probably will next time I sit down at the scope. Anyway, it's been interesting to work on this. This is like the first Pro-Am project I've worked on. He's a professional. Half of the people in this group are professionals. And just because he called the task doesn't mean that it's any less a Pro-Am operation. And he goes through the work that he's doing every other week to tell us what's going on. He's modified his theory a little bit in the last couple of weeks with all the data that he has gotten. So it's interesting to hear and see his discussion of the results so far. So when I took up this quest, tilting at windmills, that doing a little Pro-Am work might be kind of interesting. Didn't have any idea at the time, but it is proving to be interesting. mainly because he's so close to us and able to, relate his analysis and what he'd like to do and see next. So there you go. That's what we've got. Your club dollars at work.
Yeah. Get you some more posters. He wants posters.
That's all I had.
You get acknowledgements on the paper.
Oh, yes, actually, well, he will write a paper. Thank you. And anyone that contributes along with the name of their observatory will appear in the paper. Yes. Thanks for asking.
It's like, I want some credit.
Pass our meeting.
Thanks, everybody. Very interesting stuff.
That's it.
Who knew?
Yeah.
You do actual science at some point. Probably not before I retire again, being chief spectroscopist.